So today I would like to, so this is a little loud, isn't it? I would like to speak about the thermal history of the universe. Of course, I have too many things to say in too little time, but we'll try to give you a feeling of what's going on and how thermodynamics, or more exactly, statistical physics is applied to this kind of field of study. Now, before I do that, okay, let me remind you that next week we will have review sessions. I will give a review sessions Wednesday, 4 to 6, 325 LeConte. So this is in the east part of LeConte. Slight possibility that I'll be stuck on a jury, but relatively small. Okay, and then Alex will give a review 1 to 3. Somebody wanted to specify PM. 8 Lewis. Okay. The 8 or 9? Okay. 9. I have no idea where Lewis is, but you can look it up. Okay, so what I wanted to do is just finish about inflation. Then speak about the evolution of the temperature as a function of time, okay? And finally give you an idea about nucleosynthesis, how the elements, the various nuclei, have been formed, okay? And this will give us the opportunity of speaking about 3 important aspects of the course. One is phase transitions. The second one is more general arguments about evolution of entropy. And third, about what happens when we are with reactions of the type A plus C giving AC, where AC is the combined body of the. So for instance, what we will do is looking at proton plus electrons giving hydrogen, okay? Or we can equally look at neutron plus proton giving deuterium. Or, okay, proton plus deuterium giving helium-3. So these kind of things, which are obviously happening somewhere in the early universe if it's hot. Okay. Any component, any compounds. I did not want to use B because, as you will see, B, I will call B the binding energy. So, okay. Yes, yeah, that's examples. Okay, so let us speak about. Oh, there was something which was very important. What I said, and this is the Friedmann equation, which is A is a scale parameter. Remember that. What is my notation? I don't know. Oh, it's over there. The physical coordinate, the universe is expanding in a way which is homogeneous and isotropic to first order. So the physical coordinates are related to co-moving coordinates by a certain expansion scale factor. Okay, A dot over A is the Hubble constant. Okay, and this is given by 8 pi over 3 rho plus constants. If the universe is flat, let's put this constant to 0. Okay, and we say all over the story, but we can measure the curvature of the universe and show that it is infinite. R is infinite. The universe is flat. Okay, so this is interesting because it relates the speed of expansion to the energy density. Okay. Now, I did speak yesterday, or whatever, Monday, no, Wednesday, we are Friday. About what happens in the early universe, this phase transition, which is actually a postulate. It is not something that we know for a fact has happened, but we believe, for reasons that I will come into, that we had a phase transition in the early universe where what was happening, for instance, as a function of order parameter, which is for quantum theories are fields, that the Landau free energy at high temperature at the minimum with this field being at 0, okay, and then suddenly when the temperature decreases, you begin this potential changes, and then you begin to develop a minimum, and suddenly the universe wants to go from here, where this Flaton field is 0, to a finite value of the field. And when it does that, there is this suddenly discover that it has a energy density. The energy is not 0. The energy is the difference between this point and this point. Okay? And it begins to expand. This energy is fixed. So rho is fixed. A dot over A is fixed. And A goes as an exponential of time. So very fast expansion that we call inflation. And we have estimates of the amount of this expansion. It has to be of the order of 60 e-foldings. 30, okay, whatever the difference, 20 orders of magnitude. Enormous. Okay. So why do we need something like that? I think these days, if you ask a cosmologist, why do we need it? It's because of the cosmic microwave background. There is a big problem which is hidden about this cosmic microwave background. Remember, this is the radiation from the plasma in the early universe. The plasma at a given temperature, about 3,000 degrees, the plasma, which is made of proton and electron primarily, recombine into hydrogen, and suddenly the universe becomes transparent. Okay, and what you see is basically the same thing as you when you look at the fog on the Golden Gate. You see the edge of the fog. Okay, when we are the proton and electrons are free, the photons cannot travel very far. They scatter all the time on the electrons, and then suddenly, when the hydrogen forms, the universe becomes transparent. Okay, so now there is a big problem which is hidden, and I don't have very much time to tell you in detail, if we look at the temperature of the microwave background in this direction, it is the same within 10 to minus 5. Okay? If you try to extrapolate back to the Big Bang, these two places should never have been in causal contact. So how do they know to be at the same temperature? Okay. So that's really the problem that we have, and that people recognized in the late 70s, is we had no, okay, we knew that the microwave background was basically the same in every direction. At that time, nobody could measure any difference. Okay? How could these two regions of the sky be in causal contact? How could they speak and say, yes, we would like to have the same temperature? Okay? So that's really the problem. So this is solved by the inflation, because if I plot the scale parameter as a function of time, the scale parameter, the universe, this was a Big Bang, and we don't particularly care exactly, or we do care, but we don't know what was happening there. And then suddenly these things, the universe changed by, I said, by 20 orders of magnitudes, or 25 orders of magnitudes. Okay, so things were very close in the past and were in causal contact. Okay, and then suddenly the expansion of the universe put them very far apart. In general relativity, there is no problem having the space expand with a velocity greater than the velocity of light. Okay, so that's not a problem. Okay, and things are getting away at speed which are greater than the speed of light and drop out of causal contact. Okay, so that was the main reason for inflation. We need something where the universe expand extremely rapidly in the early universe and somehow settles down. And that's the idea of a phase transition. It occurs at a given temperature, and after that, you are done. Okay, so you don't have to. So this was discovered simultaneously by Alan Guth at MIT, a good friend of mine, and Starobinsky and company in what was Soviet Union at that time, and then there were lots of discussions about. Now, in detail, it's very difficult to do because phase transitions are notoriously difficult. You have bubbles forming. You have to prevent bubbles to form in the universe, destroying the isotropy that we see, and so on. Okay, so there are lots of things. But then the byproduct is that you explain then naturally that the space is flat, because whatever curvature you had to start with, you expanded this curvature very much by this 10 to the 25th expansion of the universe. This curvature will scale exactly in the same way, and for all practical purposes, the space is flat. Okay, and so you don't need to worry about initial conditions. And the third thing, which is important, is that you have quantum fluctuations of this field phi, which are frozen, and which will provide a seed for density fluctuations and the formation of galaxies. One thing which is absolutely amazing in cosmology is the following. If you plot what we call the power spectrum of density fluctuations, okay, as a function of the spatial frequency. or wave number that we call k. We just Fourier transform or make a harmonic analysis, depending on your, of the density fluctuations in the universe as a function of scale. We have a power spectrum which is something like that in logarithmic scale. Okay, we can measure that very well now. Okay, and we understand the shape. Now, if we measure the microwave background, cosmic microwave background, on this plot, it's over there. But then if we extrapolate by just the expansion factor that we know about, this, okay, these things lie right there. So the fluctuations that we see in the cosmic microwave background link perfectly with what we measure in the galaxies, in clusters of galaxies and so on, in terms of structure. And so what we that was the great excitement about the cosmic microwave background in 1992 when we first measured, George Smoot and John Mather measured these fluctuations. They were right where we needed them to be to understand. So we were observing the seed of the. Okay. So I'm sorry, this is supposed to be scale. So we have no real mechanisms. It's just a possibility, a generic possibility. We don't have a theory which says, yes, the inflation should occur because we need this field. It's just an example of how cosmology points to physics at the very high energy, much higher. We are speaking of physics at 10 to the 16 GeV. That's the order of magnitude that we need. Okay. Our best accelerators are 10 to the 4 GeV. Okay, so we are 12 orders of magnitude above accelerators. Okay, one of the reasons I did switch to cosmology, I was not ready to wait for a 10 to the 12 improvement. Or it was 10 to the 14 at the time I was in particle physics. I was not ready to wait for that 10 to the 13 improvement. Okay. What can we test? Actually, that's very beautiful, but what we could test. So actually, there are several things which fall right into place with inflation. So most of us really think that inflation has something to do with reality. But the holy grail would be to see gravitational waves from this inflation period. And that is possible by looking at the polarization of the microwave background, and this is what people are doing these days, trying to measure more and more accurately the polarization of the microwave background, and that so inflation occurs at very high energy, but there are particle consequences that you can test in principle. Now, I should stop there, but this is very much related to all the discussions that you see in the newspapers and on television about multiverses and so on. Okay, as soon that you could have regions of space where they have phase transitions, you could generate inflation and another, what we call baby universe. Another universe will emerge from the current universes. Okay, so there are lots of speculation. How do you test that? Okay, that's really the problem for the experimentalists. Okay, so I think I probably said enough about inflation. Let me just ask you a few questions so in our space, if we look at the sphere, for instance, which is moving with the expansion of the universe, co-moving with the expansion of the universe, this sphere increases of radius as a function of time. Okay? But now, if I go to the x space, I divide the expansion, and in the co-moving coordinate, this sphere has fixed radius. So now, what is constant in this co-moving sphere or volume, during expansion? The energy, the entropy, or I should have said the energy, the entropy, or the temperature. Okay. Okay, I'm a little disappointed. Why am I disappointed? Okay. There are several. Okay. Let me stop. The result is the entropy. Because the energy cannot be constant because this sphere is working against the rest of the universe. Okay, there is a pressure. Okay, so the volume increases minus PDV acts, the amount of work on the outside is PDV, or the energy inside is decreased by minus PDV. Okay, so the energy has to decrease. Now, the entropy, on the other hand, should not decrease because if the universe is homogeneous and isotropic, there is as much heat transfer one way and the other, and therefore, yes, you are. Yeah.
So what is the universe doing work on?
The rest of the universe. So my sphere, when it is expanding, there is the net work of the force of the pressure is positive. Okay. So there are lots of subtleties. Yes.
Okay, so we're just picking like a random sphere.
In a random sphere.
Doesn't it include the entire?
No, it's just a fraction of the universe, and I'm assuming that the universe is isotropic and homogeneous. So there is a universe which is kind of, okay, that's a, so this, okay, so anyway, maybe we learn a little bit of physics there. Okay, so that's the entropy, if the universe is uniform and isotropic, there is no heat transfer. Net, there is no net heat transfer. Okay, so the entropy doesn't change. And the process of the expansion is, if you don't have a first order phase transition, which would be not reversible, there is no production of entropy. In some sense, if you like, in old language, the expansion of the universe is reversible or quasi-static, whatever language you want to. You stay in thermal equilibrium. Yes?
So wouldn't this imply that the energy of the universe goes to zero over time?
Yeah.
So how would does that mean the universe would
Okay, so we have to be a little careful. That's the energy in that sphere. It goes to 0 over time, but okay. You would get me there because there. Yes, no, universe, the energy of the universe goes to 0 over time, yes.
So does that mean at a certain point the universe stops?
If it's flat, indeed, and if you have no vacuum energy, which is the other problem, yes, A of t versus t, if it's flat, you can show that it will coast at infinity. It will be, it's a parabola, okay, A of t is a parabola and just stops expanding. And you can understand why this is occurring, okay, modulo the vacuum energy, is because stuff inside the universe is slowing down the expansion by gravitational pull. So the expansion was expected to slow down. Now, the surprise that we had in '98 is that we have evidence that the universe does something like that. That is, that instead of decelerating, it's accelerating. Okay. And that's due to vacuum energy. And vacuum energy, so that's an interesting thing. Some people are saying, oh, be careful, guys. We are getting into a inflation period. And maybe one of these days, our universe will expand by 10 to the 20. And we'll be gone. Anyway, unlikely because we don't think that this physics is present at this temperature. But okay. So this tells us actually the way we do that. Okay, I have to be careful about time. Okay, I have a few minutes for that. Is that, okay, so you remember we did show that the energy density for relativistic particles. Okay, so in the early universe, a number of particles are relativistic, and the entropy is totally dominated by the relativistic particles. Okay, and that the energy density for relativistic particles goes as t to the fourth, and there is a number of degrees of freedom, which is 1 for each polarization for bosons, and 7/8 per polarization for fermions. We did that a few days ago. Okay. And similarly, the entropy, which density that I call small s, I think. Okay, or small s equal sigma over v will go as g star t to the cube. Okay, instead of and that's basically related to the number, very much related to the number of relativistic particles. Okay, so if my so what is the sigma by comoving volume? Okay, the volume of the comoving volume okay, the moving sphere, is equal to the volume, the physical volume divided by a cube. Okay. So in that case, we have a sigma, so S comoving, which is, oh, here it is, S comoving, which is sigma over V comoving, which is A cube of T, sigma over V, which is proportional to G star T cube. Okay, and we said that the entropy in this comoving volume is constant, so density is constant. Okay, it has a fixed radius. Okay, so what you get is that T goes as 1 over A of T. The temperature goes as 1 over the scale parameter. And this is exactly also the results that you get in general relativity. In general, you can, instead of speaking of comoving entropy, you can look at the velocity of the particles, or the number of particles, and so on. Okay, and you can make the calculation, and that's the results that you get. So the reason why the temperature goes as 1 over A of T is related to the Doppler shift. As the universe expands, the velocity, the wavelength of the photons, for instance, of the relativistic particles is stretching out, and in general relativity, and basically the wavelength increases, the frequency decreases, therefore the temperature decreases. Okay, so anyway, if there is no change of degrees of freedom, T goes as 1 over A. So I have, this was actually, okay, what I used in this graph, when I extrapolated from there to there, I used the fact that the temperature, we can compute from first principle that the temperature at the time of formation of hydrogen of recombination is 3,000 degrees Kelvin. We measure about 3 degrees Kelvin now. This occurs when the universe was 1,000 times smaller than it is now. Okay. So if the number of degrees of freedom is changing, then, and that happens many times in the history of the universe, for instance, when the E plus E minus disappear to put gamma, to make photons, you have a kink in the temperature evolution. And that's, okay. I should probably go to the final point that I wanted to do, which was nucleosynthesis. Okay, so let's go to that thing. And let's call B the binding, so A plus C, two components make AC. And in the early universe, these things could go back and forth. Okay, so let me call B the binding energy of AC. Okay? So my question is, how does the proportion of AC vary with temperature? Okay, I I cannot speak English or write English late at night, apparently. Okay, how does the proportion of AC vary with temperature? So it depends. At high temperature, we cannot have AC. Or at low temperature, we cannot have AC. Okay. So, kind of split class. We don't have the time to go into discussion, but the answer was B. Okay. And it's very simple that you can think about AC if the, okay, so I should have said the binding energy is positive. Okay, this was implicit, but I'm sorry, I should have said that. If I look at the potential between A and C as a function of their A and C as a function of their radius, okay, now is the binding, this is the binding energy. And what is happening is if I'm at very high temperature, B, so if I at low temperature, the two A and C like to stay on in this potential. Okay, that's why they are bound. And at high temperature, there are thermal fluctuations which are kicking them out. Okay, so at high temperature, I cannot have a bound compound. If I, in chemistry, if you like, if I heat water at too high a temperature, it dissociate in H2 and oxygen too. Okay. So now if I'm in equilibrium, what relationship do I have? That the densities are adding up, that the chemical potential are adding up, or that I have this kind of relationship.
Are some of those sub B supposed to be sub C, and then the sub C is supposed to be sub AC?
Ah.
Or is that for a different equation?
Okay, you got me. I was really tired. Okay, so A is supposed to be mu A plus mu C. Okay. Okay, and the other one was supposed to mu A mu C over mu AC. Okay, so let's restart. And the first one, okay, A was Na plus Nc equal NaC. Apologies. No, that's not what I wanted to do. Okay. Can we vote? Two people reserve judgment. Okay. Okay, so indeed, what is the right equation is that the chemical potential adds. Okay? And there, this was a kind of trick. This is not at all, this is not an equation I know of. Replace the mu's by the densities, the n's, then you have an equation of this type, which is so-called the action mass law, the mass action law, sorry, and which is just a direct consequence of mu A plus mu C. Okay, so the problem is that I'm running out of time, but let me try to tell you a little bit how we discuss the formation of atoms of nuclei in the early universe. So, for instance, this guy, okay, so in the early universe we produce quarks or maybe something else, then it becomes quarks, becomes neutrons, protons, and electrons, okay? And at the early part of, okay, before about 3 minutes in the age of the universe, we are too high energy and the neutron plus protons cannot give deuterium. Deuterium is dissociated by the temperature. Okay? And then when we come below an energy, I forgot, 100 keV or so, the deuterium is able to stay, and we form deuterium. Okay? Then we can form helium-3, helium-4. Okay? Now we have to be a little careful for when we have two charged particles like that. Instead of being a potential like that, we have a potential which goes like that, because they are charged, and if you try to bring them together, they repel each other. So you have to go through the potential barrier to have them stick. Okay, so so you can do that at high temperature, but at low temperature, you cannot do that. The system is freezing out. Okay, so let me just show you one thing. We can use this to this kind of argument to follow the expansion of the density of various components. For instance, the neutrons, okay, you see about 3 minutes, the neutrons have decayed a little bit, and then suddenly, because we are forming in the green, where deuterium is H2H, so suddenly we are beginning to form deuterium, the neutrons just plummet, and when we are forming deuterium, we can begin to form helium-3, helium-4, okay? And then when the temperature is small enough so that you cannot go over this potential barrier, everything freezes out. So you have a very, in the space of a few minutes, you are forming all the nuclei, light nuclei in the universe. So you can measure this thing, try to measure the amount of deuterium which is left, or the amount of helium-4, and get a number of conclusion. And that's how we basically measure the density of the baryons in the universe. And show, and okay, there are lots of things that I skip. Oh, sorry. And you arrive, that's the way we arrive at the fact that this ordinary matter baryons neutrons and protons is only a tiny part of what we observe in the universe. This is dark matter, maybe WIMPs. This is dark energy, and that's okay. And that's just the ordinary matter. And by the way, the cosmic microwave background give exactly the same results with totally different physics, which is quite amazing. One of the great achievements also the last 10 years. Okay, so let me conclude. So what I wanted to conclude, I'm sorry, I was hoping to have one more lecture to go through this material, but we are a little slow. What I hope that I showed you is a link between nuclear physics at small scale and the universe, what happens at a large scale. And this, what we are trying to do is to explore the links between particle physics, quantum gravity, and the universe. That's what cosmology is about. So I'm particularly fond of a compatriot of mine, Pascal, the same of the Pascal that you have in what is Pascal matrices or whatever. It was a mathematician and philosopher of the 17th century who had very beautiful lines about the link between infinitely small and infinitely large. But now the infinitely small that we are considering is much smaller than he knew about, and the infinitely large is much more larger. And there is this nice quote from John Muir. When one tugs at a single thing in nature, he finds it hitched to the rest of the universe. So that's the thing that, and let me, I hope that I gave you a taste of how statistical physics can be put in service of frontier science. I suppose I'm very French today. That's another Frenchman, Camille Flammarion, who was a printer and made this beautiful picture of this guy going to the edge of the universe and looking at outside. And although this is essentially wrong, by the way, the Earth is flat. Somebody noticed, told me that I never noticed before. This is kind of the symbol of what we are trying to do in science. Okay, thank you. So I'll see you next Wednesday, and thank you very much for this semester.
Out of curiosity, I was wondering why inflation predicts the